Welcome back, everybody. As announced, now we have Han with how to use IPC fuzzing and variant analysis to find what is a sandbox escape in Safari. Here you go.
Okay, hi. I'm pretty nervous, so please bear with me. I'm Kichan An, and some people know me by my Twitter handle Externalist. And today I'm here to talk about some sandbox escapes in Safari. A little bit of introduction. I work for Exodus Intelligence, and I have experience in vulnerability research in various areas. And currently, I'm mainly focusing on creating exploits that constitute the Safari full chain. This is the agenda for the talk. I'll start with a short introduction on IPC internals and talk about the attack surface and move on to fuzzing, and finally discuss variant analysis. The first topic is the attack surface. There are essentially two sandbox profiles that govern the Safari web content process, and it's these two files. If you look at these files, there is a really long list of fine-grained policies. That's a little over 1,000 lines. However, the only ones that matter in terms of sandbox escapes are the ones that start with allow Mac lookup, because they list the IPC endpoints that are reachable from the Safari sandbox. And if you collect all of these endpoints in the profile, you'll realize there's a plethora of endpoints that an attacker can choose from. And I think Apple has realized this is a problem. And if you look at WebKit commits recently, they're starting to add lots of telemetry to find out which IPC endpoints are not being used. And they're removing the ones that they determined obsolete one by one. Personally, what I do next is I organize the attack surface in different categories and map the service endpoints into actual binaries. The reason I do this is so I can focus on IPC endpoints that match a certain criteria. I would normally try to focus on services that are running in unsandbox context. Newly added IPC services are definitely worth checking out because they're probably less audited. And categorizing also helps if you want to look into services that use a specific IPC method, such as the legacy IPC. There are mainly three types of IPC communication. There's actually a little more, like distributed objects, notifications, named pipes, and so on. But I think these three are the most relevant. There's the legacy IPC interface that's been a target for hacking competitions for many, many years. And then there's a more newer XPC and NSXPC, which most services are based on. In this talk, I'm going to specifically focus on the legacy IPC interface, which brings us to the next section, legacy IPC internals. So why legacy IPC services in particular? The main reason is because it's been a target for sandbox escapes in multiple Pontoon competitions, so it already makes it a very attractive target. And also, when you look at various IPC services, you'll see that parsing, deserialization, and handling of the attacker IPC data is different and unique for every service, which makes it more prone to coding mistakes and human errors. And I found legacy IPC services to be much easier to understand and reverse. But yeah, that's just my personal preference. And the IPC message handling logic for legacy IPC services comes in many flavors. As an example, I'll walk through how it's implemented in the security D launch daemon. This is the main function. It calls into a function called server.run, which in turn calls to Mac server.run. This in turn calls into run server thread. And what you see in this function is the heart of the IPC message handling loop. It receives the IPC message through the Mac message function and then delegates the actual heavy lifting to the handle function. This function simply calls UCSP server. And the source code of UCSP server is not actually included in the source archive, but you can generate it with the MIG util, which auto-generates the server and client-side code for the MIG definitions. After that, you have the source code for the UCSP server function. This function essentially chooses which MIG function it's going to call based on the MSGH underbar ID field, and actually calls the MIG function. And all of the MIG function definitions are declared in a file with the .defs extension. And the most interesting ones are the ones that take a variable length and buffer as input. These variable size input buffers are most likely going to be parsed in some kind of way in the MIG function. And this parsing is usually the source of many bugs. For example, this is a MIG function called findFirst in security-D. In the very beginning of the function, there is a call into the constructor of the object. This constructor accepts an attacker-controlled variable length buffer. And when you look into this constructor, you'll see there's a lot of deserialization going. This is just a small portion of it, but there's like a huge amount of it. And this already makes it an interesting target to audit. Now, this is the infamous doc service. This is an example of a legacy IPC service that doesn't have any source code and just the binary. The thing you're usually looking for is the large function table, which enumerates all the MIG functions. And to find that, the best starting point would be to find the place where the IPC endpoint is being registered. And in this picture, the IPC service is checking into launchd with bootstrap underbar check-in. And a couple lines below, the MIG function table is being registered by the MSH create MIG server source function. Sorry for the short delay. I'm running out of breath. And this is the function table that includes all of the MIG functions. And at this point, you can either create a function targeting all of these functions, or you can just purely audit these functions one by one through pure reverse engineering. This is how a MIG function typically looks like in the binary. If you follow that inner function in the middle, you can see the main function logic. And in this example, you can see the unserialized CF type function, which was a source of a really nice bug found by Nicholas Baumstrout somewhere in this room and used in Ponto in 2019. After you located these MIG functions, you can either audit the source code or reverse engineer the service binary. It's also worth trying to attach a fuzzer if the function is too complex to reverse and you just want to get some quick results out of it. And finally, there's variant analysis. Personally, I use all 4 of these methods because they all have their pros and cons, and they tend to complement each other. First, I'll talk about fuzzing. When I first started, I tried to build something based on a set of goals, these 4 goals. I wanted it to be coverage guided because coverage guided fuzzing seems to be the latest craze, and it seems to have the highest return on investment compared to other fuzzing methods. And I wanted it to be generic, so I could just plug it into any IPC functions with minimum effort on my side. And finally, I didn't want to build it from scratch, but instead fork from an existing fuzzer, so I could massively cut down on development time. The first question was which fuzzer I was going to use as a base, and these are the 3 most popular fuzzers. AFL is like the industry standard nowadays, but unfortunately, it isn't really fully supporting macOS at the moment. Then there's libfuzzer, but however, you need source code to use libfuzzer, and Apple releases source code for only a small portion of their userland daemons services. Finally, there's HongGFuzz. Personally, I think HongGFuzz is pretty underrated because if you look at most fuzzing projects, they're pretty much some kind of fork of AFL. But I think HongGFuzz is very stable, feature-rich, modular, and the source code is pretty easy to read and modify. And most importantly, it fully supports macOS, so it was perfect for this project. So I decided to build my fuzzer based on HongGFuzz. There was actually some previous research done by Paul Hernault in the past. The basic concept is he used Quark's Lab's dynamic binary instrumentation framework, QBDI, to attach a coverage-guided fuzzer to closed source binaries. And the way it works is basically it works the same way as WinAFL. WinAFL tries to achieve coverage-guided fuzzing by inserting callbacks in every basic block using Dynamo Rio framework, while writing to the feedback bitmap in all of those basic block callbacks. Okay, so Paul did pretty much the same thing, using QBDI instead of Dynamo Rio, and use Hongji Fuzz as the main driver for fuzzing. And with that, fuzzing macOS library or framework functions becomes as simple as writing a couple dozen lines of code. I'll do a small case study with the unserialized CF type function that's called inside an IPC function of the infamous doc service. Paul didn't release the source code of how he implemented the glue between QBDI and Hongji Fuzz, so I wrote my own version of it. On the upper half, it's initializing the QBDI framework and deciding which library code it's going to instrument. On the bottom half, there's a Hongji Fuzz persistent loop, which calls QBDI call. And that in turn kickstarts the unserialized CF type function call within QBDI's virtual machine. The fuzzing input is provided by Hongji Fuzz by the hf__ iter macro. This is the function that will be called on the beginning of every basic block. Basically, the function just marks the feedback bitmap and simply returns. This feedback bitmap will be interpreted by Hongji Fuzz, which in turn drives the feedback-driven fuzzing engine. I'll show us a small demo of how this works in practice. The target function is the unserialized CF type from the doc service. And I'll run this, and the demo is running on a vulnerable version of the unserialized CF type function. So yeah, I didn't have that much faith in the demo god, so it was recorded. So first, this is how it was written. This is the basic block callback function that marks the feedback bitmap. And this is the Hongji Fuzz persistent loop. Wait. Yeah, right there. And it's calling unserialized CF type. And there is only one file in the input corpus, and it's just a simple core foundation dictionary that I filled up with random keys and objects. When the fuzzer runs, it quickly finds several crashes, and Hongji Fuzz will in turn, yeah, it's running. And Hongji Fuzz categorizes them in a separate folder. And I made a small verifier that tests each of these crashes. And what it does is it simply calls the vulnerable CF unserialized CF type function. So I copy the first sig-il crash case and verify that it's an actual crash case. And the next thing is to try again in a debugger. And printing the backtrace shows the root function of the vulnerability, CF attributed string create with runs. And further printing the register values show that it's probably a very interesting crash case. Yeah. Okay. Okay, whatever. So yeah, this was actually a bug that I found somewhere in late 2019, but it was sadly burned due to a bug collision from Pontoon. But yeah. So I think the beauty of all of this is that in order to run this fuzzing session, I didn't have to modify any of Hongji Fuzz's source code, and all of it works with just a couple dozen lines of code. But not all code is neatly wrapped up into a function in a framework or library function. So I think the next logical question would be, how do you fuzz functions that are compiled inside the service binary? And if the function is pretty self-contained and doesn't rely on the daemon to be actually running, then it's possible to fuzz using the previous method that I just described. But what about functions that properly work only when the daemon is actually running? And a nice alternative to that would be in-memory fuzzing. But wouldn't it be awesome if we could somehow hook it up with Hongji Fuzz so we can use its coverage-guided fuzzing powers? So that led to the next project. So what I did was I modified several hundred lines of Hongji Fuzz so it wouldn't use its fork server model, but instead interact with a live running daemon through several IPC channels. First, Hongji Fuzz injects a dynamic library into the daemon that's already running. The dy-lib is essentially the lib hfuzz component of Hongji Fuzz and includes all of the client-side fuzzing code. The dynamic library runs its constructor and waits for Hongji Fuzz to pass all of its file descriptors. Hongji Fuzz passes several of its file descriptors that are relevant to fuzzing through Unix domain sockets. The client duplicates all the file descriptors into hard-coded file descriptor values that Hongji Fuzz expects. Hongji Fuzz then sends its exception port service name and thread number through a TCP socket. The client receives the exception port through launchd and registers all exceptions to be handled through the exception port on the Hongji Fuzz server side. And this will make Hongji Fuzz handle all exceptions happening inside a separate service. Then the client initializes the QBDI virtual machine and runs the Hongji Fuzz persistent loop. Although the code is to wire all of these together is pretty hacky, it surprisingly works correctly. And the files are passed through the files to be fuzzed are passed through a shared file descriptor, and the persistent loop state machine is pulled through another shared file descriptor that Hongji Fuzz interprets. Within the loop, the client essentially just calls the target function through the function QBDI call. This runs the function through the QBDI virtual machine, and the basic block callbacks will mark the feedback bitmap, which is also shared between the server and the client through file descriptors. Actually, there's a little more to this, but this is basically the gist of it. And I would like to give a special thanks to Nicholas Baumstrock for this tweet, which inspired me to start this small fuzzing project. And as much as I want to, but I couldn't actually disclose 0 days live on stage, although it would be super cool. So I'll just fuzz a non-vulnerable function just to show a demo of how it actually works in practice. And in this demo, I will fuzz a deserialization routine in security pretending that we don't have access to the source code and just the actual binary. This is what the function looks like in the binary. And I reverse this function just enough to pinpoint where the deserialization is happening. The fuzzer is going to target the function I labeled as copy in, and the Hongji Fuzz persistent loop will feed data into the second and third parameter of the function, which is a serialized data buffer and size. The fourth parameter points to the deserialization routine. So a short demo of how this works. Okay. So this is the code of the libhfuzz dynamic library, which I heavily modified. And these are the offsets of the uh, various deserialization functions I found through reversing. And the one that's highlighted is the qbdi call function, which actually calls the function through qbdi. Oh, I was looking, there was a screen right there. So yeah, this is where the client receives various things from the HongjiFuzz server. Yeah, it first receives all the file descriptors through a Unix domain socket. Then it receives the exception port service name and the thread number, duplicates all the file descriptors, and maps them all into memory. And finally, it sets up the exception port. And the next thing is the seed corpus, which is just a single input that I collected with Frida and saved to a file. And as soon as the fuzzer runs, the fuzzer will quickly converge into a state where it fully explored all the paths that's reachable by deserialization. And the files in the input directory, corpus directory, reflects the results. And we could test more deserialization functions just by modifying the function offset, like I'm doing in this example. And then run make and run the fuzzer again. And the fuzzer, again, quickly converges into a state where it explored all paths. So yeah, that's pretty much it. So yeah, although the demo didn't really show any new bugs, it actually works. And there's nothing super advanced, like it's just a coverage-guided fuzzer attached to a live running service. And I think if you point this to some complex parsing routines or deserialization routines in other services than the ones that were presented here, you might find some interesting bugs. Yeah. So yeah, that's it about fuzzing. And the next topic is variant analysis. There was actually a really good talk by Matty Stone at Blue Hat IL about a week ago. That's also a topic about variant analysis, and I highly recommend for anyone who's interested to go through it because it's a pretty good talk. So for me and for many others, I believe, variant analysis is equivalent to searching for low-hanging fruits. I think it's the modern version of searching for low-hanging fruits. And if you look around Twitter or talk with other researchers, you'll recognize that a lot of people are actually doing this. And this is a quote borrowed from Bruno Key's talk, and I couldn't agree more to this. Apparently, lots of people are doing this, so bug collision is really a thing. So this is basically variant analysis 101. First, you pick a good reference bug, preferably a bug that has an exploit attached to it. Then you study the component that contains the faulty code. And next, you try to understand the root cause of the bug, studying everything you need to along the way. And while you're doing so, you'll get a general idea of the attack surface where similar bugs can occur. And finally, you start looking for new bugs with the similar bug pattern. And I'll discuss how a researcher goes through this process by looking at two real-world bugs. The first bug is actually not really a sandbox escape, so it might seem a little off topic. But JavaScript, it's a JavaScript core bug. But still, I thought it was a perfect candidate to discuss variant analysis while not straying away too much from the topic of browsers. And also, I thought it was a really cool bug back then, but there wasn't much public interest into it. So I wanted to use this opportunity to discuss more about it. So this bug family was first found by Loki Harty back in late 2018. And I call it the does.gc bug family because the does.gc function is the mothership of this entire bug class. So this is Loki Harty's public advisory. It was a pretty cool bug. I mean, it was pretty cool that he found this bug through just pure source code auditing. And a couple months later, Luca posted his own variants on Twitter, and along with a proof of concept exploit. And this is the patch that killed Luca's variants. It patched 6 DFG opcodes that were incorrectly returning false in the does.gc function. Now, I'll go through the process of understanding the root cause of this specific bug. There's this function called does.gc, and what it does is it's responsible of telling the DFG compiler which DFG opcodes have the possibility of bringing up the garbage collector. And before the patch, the compare EQ opcode was returning false, which means that it doesn't have any chance of inducing garbage collection. Now, this is how the compare EQ DFG opcode is compiled into the DFG JIT code. It flows into the function compare. If both arguments are string type, then it'll eventually flow into compile string equality. If any of the arguments is a rope string, then it'll flow into operation compare string EQ, and which goes into these 3 series of function calls until it reaches here. And if any of these arguments, if any of the arguments is a rope string, then the function will try to resolve this rope string. And doing so will create a new buffer that's big enough to contain all of the strings that are contained inside this rope string. And this new allocation is what could summon the garbage collector. So the fact that JITted code can reach this piece of code, which creates a new allocation, violates the assumption that compare EQ opcode can never bring up the garbage collector. So why is this a problem? To explain why, it's important to understand a DFG optimization phase called DFG store barrier insertion phase. And simply put, that phase largely relies on the correct modeling of the does.gc function. And if does.gc isn't modeled correctly, the optimization phase will not emit something called write barriers, where it's supposed to emit them. And these so-called write barriers are important to make garbage collector work properly. So a single missing write barrier can turn into a serious problem. So let's assume that we are back in time, like right after we saw Luca's tweets that the bugs were patched. And at this point, you would start thinking, are there any more of these bug patterns in JavaScript core? Or were those the last ones standing? You can quickly figure out by investing a day or 2 in source code auditing. And so here are the ingredients. There's a giant switch case in the does.gc function, and the opcode that you're looking for must return false. And the JIT code that's emitted by the opcode must create a new allocation. Also, the size of the allocated object should be preferably controllable. The ideal case would be an opcode that would resolve a rope string or something similar. And finally, the JITted opcode should not hold the lock of the garbage collector. There are actually a few functions that explicitly hold this lock in order to prevent these kind of issues. And to give you a perspective of how I found and how anyone could have found a variant of this bug, what I did is I just manually read the JIT implementation of every single DFG opcode for a couple hours, being very mentally focused to find code that matches this exact same pattern until I reached the has index property opcode. As shown in the picture, the does.gc function used to return false for this opcode. And this is how the opcode is compiled by DFG. If the opcode passed along is not an array object, then the JITted assembly will jump to a slow case. It calls through a series of functions until it tries to call the getOwnProperty slot by index function inside the JSObject method table. And if the object happens to be a string object, then it further goes down the chain of function calls until it resolves a rope string. This happens when the object is a string object, but the string object is actually storing a rope string instead of a normal string. So this is essentially a variant of the patch does GC bug class. And unfortunately, this variant didn't live very long. It lasted for about a month until it was patched somewhere in March. And somewhere around May, a bug was de-restricted in the Project Zero issue tracker, and I realized that Samuel Gross reported the same bug to Apple in March. So yeah, this proves that bug collisions are real. But regardless of bug collision, and I think the morale of this story is that it's relatively easy to find bugs with a very specific bug pattern. And what you have to do is you just have to read the source code with a trained eye and being very focused to look for an exact bug pattern. And of course, this requires a lot of patience and perseverance, but it's very doable. So yeah, nothing really terribly advanced. And here's how Apple tried to eliminate this entire class of bugs. It would take too long to explain exactly how it works, but they placed asserts that would check if the does GC function and the allocations happening inside the JIT code is correctly modeled, and it matches what the JIT is assuming. And however, if you look at new DFG opcodes, most notably the big integer DFG opcodes being added every now and then, you can see that some of them are still being incorrectly modeled in DustGC. But Apple seems to be running an internal fuzzer, which catches them through these new assert statements. And after a couple of weeks, you can see, if you see the WebKit commits, they're moved back to the right switch case. So maybe, I think this is the end of this class of bugs, but who knows? Before moving on, I want to briefly discuss how this bug class can be exploited, because it was pretty cool when I saw it first. When Lucas variants were patched, he just dropped the POC on Twitter and just moved on to his next thing. And I thought it was a really cool exploit, but I haven't seen anyone talk about it in a public domain. So I thought it would be worth discussing it here because the exploit technique behind it was really nice, in my opinion. The exploit assumes that the garbage collector runs in a single thread, but there are ways to make it work in a multi-threaded environments. This function called ralloc creates an enormous tree of arrays. And the purpose of this tree is to make the garbage collector traverse the tree in a kind of a little bit like a breadth-first search. So it'll take a long time to reach the leaf nodes. And due to the searching algorithm, the most left bottommost leaf node will be reached in the very last iteration. And we'll assume that this left bottommost leaf node is storing a valid JS object. Victim is just an array with 8 elements, and victim1 now points to the root of the enormous tree. And this compiles into the compare less DFG opcode, but the does GC function returns false for this opcode. So DFG is not aware that this opcode can actually bring up the garbage collector. And because of this, the logic behind the DFG store variation insertion phase concludes that it doesn't have to insert the right barrier after this piece of line. And this right barrier is supposed to put the victim array back onto something called the mark stack. So the garbage collector would visit it once more, but in this case, it won't. So what can an attacker do with this missing right barrier? Let's assume that the function argument S is a rope string that's very, very long enough to wake up the garbage collector when the rope string is being resolved. And when the compare less opcode executes, it'll kickstart the garbage collector because resolving the rope string will create a very huge allocation. And the mutator, which is the JavaScript executing main thread, will collect the core constraints from the stack and pass it on to the collector, garbage collector. And before the mutator even reaches this piece of line, the collector will already have marked all 8 elements of the victim array. The garbage collector is still traveling through the enormous tree, marking each node one at a time, and it hasn't reached the left bottommost node yet, which is storing a valid JS object. And before GC ever has a chance to reach this left bottommost node, the mutator snatches it and saves it into victim 0. And at this point, the garbage collector already marked victim 0. So there should be something that should notify the garbage collector that it should go through the victim array once again so it could mark that updated victim 0. And that something should have been the right barrier. That should have been inserted right after this piece of line, but it's missing now. The right barrier is, of course, missing, so the victim array is not placed back on the mark stack, and the mutator stores the constant 0 in the left bottommost node of the enormous tree, which originally contained the JS object. At some point later, the garbage collector finally arrives at this left bottommost node, and it'll only see the constant 0. So now there is a valid JS object in victim 0, which isn't marked by the garbage collector. And the garbage collector won't revisit it again. This victim array is returned to the caller. And the caller keeps allocating JS objects that are exactly the same size of that unmarked JS object. And at some point, the unmarked JS object will be swept and reused for a new allocation for one of the objects that's going to be stored in the variable z. And at that point, a valid JS object, which used to be in the left bottommost node of the enormous tree, is overwritten with a new JS object with the same size. And there's actually a little more to this, but yeah, I just abbreviated it in one sentence. But basically, the exploit makes a stale JS array object to point to a hex 200 size buffer, where the indexing type is contiguous JS values. And there's another valid JS array with the array's buffer overlapping the same hex 200 buffer, but this time the indexing type is contiguous doubles. So essentially, there's 2 arrays where with different indexing types pointing to the same underlying hex 200 buffer, and this creates a perfect condition to create the fake object in the address of primitive. So yeah, mad props to Luca for this super interesting GC racing exploit technique. Yeah, and the next case is going back on topic, and it's a Sandbox escape that was posted last year in April in the security team blog. This bug was found by a researcher called Mohamed Gannam. So it's an uninitialized buffer vulnerability in the PowerD daemon, which is running as unsandbox root. It was actually a really neat sandbox escape that was pretty well engineered. But like most sandbox escapes, I think it was pretty underrated and didn't receive much attention by the community because the jailbreak community is always just crazy about TFP zeros. And it was actually a bug that was very easy to miss unless you were looking very closely. And I'll do a brief root cause analysis about this bug. This is the IPC main handler function of PowerD. And you can see that it allocates space for the output buffer, but it never initializes it to 0. And the make function will be called passing this uninitialized buffer. And in a make function called IOPM last wake time, there is a check if a global variable is not null. And if it's not null, then the function forgets to initialize 2 values in the output buffer and sends them back to the caller. And this gives an info leak of primitive of a couple of bytes. And this one was pretty funny. It's in this MIG function, IOPM connection copy status. The function does absolutely nothing and returns. And this leaves the output buffer pointer and the output buffer size uninitialized. And the end result of this is that whatever address was stored in the output buffer pointer is interpreted as the start of the buffer to send back to the user. And whatever uninitialized value was in the buffer size is interpreted as the buffer size. And the buffer data will be sent back to the caller, and this effectively creates a massive heap info leak primitive. And last but not least, there's IOPM HID event copy history. If the CF property list create data function fails for data stored in the global variable GHID event history, then it returns current success without initializing array data in array data len. And because the MIG definition specifies the dealloc flag for this function, the MIG function is going to deallocate the output buffer array data after it returns. And this essentially creates an arbitrary free primitive. So how did Mohammed Gannam exploit this? Just to give a brief overview, first you spray a lot of large core foundation objects, and then using the info leak one of the core foundation object's address, and then use the arbitrary free bug to deallocate the leaked core foundation object. And afterwards, refill the arbitrary freed memory with page-aligned and carefully crafted payload that holds the job chain. And finally, call a MIG function that calls CF release on the refilled memory, interpreting it as a core foundation object, which eventually kickstarts the job chain. And the exact details of the exploit can be found in the full-blown exploit that was published by Mohammed Gannam. It's worth reading. It's pretty cool. And now let's find a variant of this exact same bug pattern in the same PowerD daemon. First, the MIG arguments must include the output buffer, and the function must also not initialize these output buffers in the beginning of the function. Also, the MIG definition must specify the dealloc flag in the function definition. And next, there must be a way to fast fill or early return so the output buffer variables are not initialized to some kind of value in the middle of the function. And finally, the function must return current success, but all MIG functions in the PowerD daemon is returning current success. And all of this might seem very tight restrictions because all of these conditions must be satisfied all at once, but it just so happens that 100 lines below the vulnerable IOPS update power source function, there's a function called IOPS copy power sources info that actually matches all of those conditions. So let's dig into this function to find out if it's exploitable. It first creates a new core foundation array and iterates over the GPS list array, copying over the description field into the array. Then it creates a core foundation property list based on the new array contents. If the CF property list create data function somehow fails, then it's not going to initialize the output buffers PS, PTR, and simply returns current success. And because the dealloc flag is specified in the MIG definition, MIG will be responsible of automatically deallocating the buffer upon return. So the conditions to trigger this bug is to fill in the GPS list array with attacker-controlled objects, and somehow make the CF property list create data fail. But where does GPS list come from? It comes from another MIG function called IOPS update PS power source. And this function essentially deserializes attacker-controlled data using the IOCF unserialized function and stores it into the description field of the GPS list array that I mentioned earlier in the slide. So that solves problem 1, but what about problem 2? The problem is that the unserialized object that comes from IOCF unserialized is passed on directly into CF property list create data. And both functions are meant to be dealing with the same family of core foundation objects. So there doesn't seem to be any chance for one function to succeed and another to fail when both functions are essentially just processing the same family of objects. But it's always good to verify an assumption if it's true, even if it strongly suggests otherwise. So looking at the deserialization of IOCF unserialized, you can see that it deserializes several types of core foundation objects. But you can also notice that it's not fully inclusive, meaning that it only includes a subset of the core foundation objects. So now this is the function CF property list create data. This function eventually calls through a chain of function calls until it reaches CF binary plist write, which accepts these kind of objects. If you draw a set diagram of the two functions, you can realize there's exactly one core foundation object that's unserializable in IOCF unserialized, but not processed by CF binary plist write, which is a core foundation set object on the leftmost side. So now the answer is clear. The attacker has to include a single core foundation set object in order to make IOCF unserialized succeed and CF property list create data fail. And the end result is another arbitrary free bug in the same daemon that is exactly the same bug pattern that Mohammed Gannam found and exploited. Unfortunately, at some point, Apple eventually demolished all of these bugs in the PowerD with a 3-liner patch. What Apple did is they basically wiped the entire output buffer with 0. So before passing it down to the MIG functions. So yeah, there goes all of the uninitialized variable bugs in PowerD. You can follow the trails of Mohammed Gannam by looking at the Apple advisories. He was actually going after a similar set of bugs in another daemon called config_d. And with a quick patch diff, you can see that he was basically looking for the same set of uninitialized output variable bugs in the config_d daemon. And these bugs were also interesting because they open a potential avenue for port replacement bugs. But yeah, they're all patched now. So yeah, here are some of my thoughts on variant analysis. Variants of existing bugs can live on for several months or even years. However, bug collisions do happen very often, so you should brace yourself for the impact. And vendors seem to be doing it very actively nowadays. And the overhead for finding bugs is relatively small compared to other bug hunting methods. And also, if there's a full-blown exploit for the original bug, then exploiting a new variant of it is very trivial. Finally, variant analysis is not only useful in finding a similar bug variants, but it also helps in knowing where other researchers are looking to find their own set of bugs. Here are some sources for variant analysis. My most favorite one is the Project Zero issue tracker, especially because they find a lot of very unique bug patterns, and almost every bug comes with a POC of some form, or sometimes even a super detailed blog post, so it really helps in terms of research. And my next favorite one is the CDI advisories. The descriptions give huge hints on where exactly the big bug exists. They sometimes just throw out the function names. And if you search for specific terms like pwn to own, you can get a glimpse of where other researchers were digging to find their set of exploitable bugs. And I think recently the CDI published a bunch of interesting bugs for VirtualBox, if I'm not mistaken. And although not very descriptive and sometimes misleading, vendor advisories sometimes help. And some security patches are very hard to reveal or patch diff and dig out. But for others, if it doesn't take too long to find the root cause based on binary or source diffing, then it's definitely worth investing a little time and taking a glimpse at the patch bugs. And blog posts also are very good sources for mining exploitable bug patterns or attack surfaces. For this Chinese blog post, I barely know any Chinese or read Chinese, but Google Translator is awesome. And of course, commits from open source projects like WebKit are worth reading. And I do a quick skim on commits every morning just to see if there are any patches that are security issues that I can base my variant analysis on, or if a new mitigation or a new attack surface is being added to the code base. And here are some questions I ask myself when I'm looking at other people's bugs. I try to find out what the attack surface was for the bugs used in hacking competitions. Then I ask myself, how would the bug finder would have found those bugs? And I imagine if the bug would have been feasible to find was a fuzzer, or if if so, then how the attacker would have designed his fuzzer to find this bug. And if it isn't, then if it would have been practical to find this bug only with pure source code auditing or reversing, or if it would have been too complicated to do so, or if it was just a variant of a known bug pattern, or if it was already a known bug that hasn't been downstream by the vendors, and so on, like the recent mobile Pontoon in 2019. And here's an example of a Pontoon bug. I think many people already read this excellent blog post from PhoneHex. It explains an integer overflow that occurs in the array spread operation, which was used to compromise the Safari renderer in Pontoon 2017. And right after reading this blog post, if you ask this question to yourself, what about the JIT code? Is it properly implemented in the JIT code? Then maybe some of the people would have found this bug that was used for 2019 version of Pontoon. So yeah, finally I asked myself, how would I have found the same set of bugs with my current skill set? What would have been the most time-wise feasible way? And after doing some self-reflection, I update my bug hunting strategies if there are any areas for improvement. And speaking of areas of improvement, this presentation only scratched the surface of hunting for Sandbox escape, in my opinion. For instance, I only went through one open source daemon that used to have an uninitialized output buffer vulnerability. The next obvious question would be, what about closed source daemons? Would they have the same bug pattern? And also, this talk only focused on legacy IPC daemons, but other daemons that use different IPC mechanisms is definitely worth checking out. And also, there are probably legacy IPC daemons that only exist on iOS, and those are definitely interesting targets as well. And finally, you can see that I haven't even attempted to attach dynamic sanitizers such as LiveG malloc. And attaching a sanitizer also gives a high return on investment, so it's definitely it's an avenue worth checking out. And yeah, I think I'm running out of time. Yeah, I'll just go through this really quickly. And this is my final comments on variant analysis. It's definitely a lower entry point for bug hunting. Basically, you just have to understand why the bug is occurring, and with a trained eye, search for that exact same bug pattern. However, like I mentioned previously, the bugs are very short-lived. And in my experience, I mean, it may be different for everyone else, but maybe like 20 to 30% of bugs are very long-lived, and the rest die pretty quickly. And I believe this percentage is gonna get lower and lower as time passes, because variant analysis seems to be gaining a lot more attention recently, thanks to SEML and QL. And on the bug collision side, I think the key is the only way is to not get too discouraged if it happens, because it will happen based on my personal experience. And finally, variant analysis is good if you're relatively new to the bug hunting scene, because if you have this fixed goal that is a strong motivation factor, which enables you to dig deeper and deeper into the target. And at some point, you'll stack enough knowledge up to the point where you don't have to rely on other people's bugs, and you can find quality bugs entirely on your own. And yeah, finally, the conclusion. Personally, I think coverage-guided fuzzing hasn't flourished in macOS as much as other operating systems, so there's still a lot of area for improvement. And variant analysis is a powerful and relatively easy way to find exploitable bugs, but be prepared for bug collisions. And finally, I think I'm repeating myself over and over, but studying patch bugs helps a lot because it not only reveals the exploitable bug pattern, but you also get to know the attack surface that you previously didn't know, which is a potential source of even more bugs. And yeah, that concludes my presentation. Thank you for listening. I think there's like 4 minutes, 3 minutes.
Yeah, we got 3 minutes of questions, or otherwise you can just come during the coffee break, I guess. So, do we have questions?
Okay.
Everybody wants coffee? Seems to be so. Okay, then wrap it up. And if you come up with a question, speak personally to An.